Welcome back and thank you for joining me. So in these notes, we're done graphing now. Now we're going to talk about how do we model real world situations. Okay, how do we model actual word problems, actual real life situations using exponential growth and exponential decay. The awesome thing is they're so similar. All right, growth increases by a fixed percent for each time period. Decay obviously then decreases by a fixed amount each time period. So what you'll notice about the equations, look at how similar they are. Okay, the only thing is obviously growth. You're adding that rate every time. Decay, you are subtracting that rate every time. So when you're working through these, that's going to be the key thing, is just knowing which is growth, which is decay, and then A is your initial value, is your starting amount. All right, and then here, obviously, that plus or minus is based on whether it's growth or decay. The only thing to remember then R needs to be as a decimal. So that's going to be the biggest thing, is you need that R to be a decimal value. So likely they're going to give you a percent. You're just going to have to know how to turn that into a decimal. All right. So let's jump right in. Let's get going on some of these word problems. A car loses value as soon as it is purchased and driven off of the lot. You buy a new Ford sedan for $12,400. If it depreciates in value by 11% each year, how much will it be worth in 5 years? So the first thing I would do is I would notice this term depreciates. Okay, you're going to need to know that vocabulary. So depreciate is going to be an example of decay. It's going to be decreasing every time period, okay? So what we're looking for in this one, decay, means we're going to be looking for that structure with the minus. The next thing I would do is I would start focusing on finding my A, which is my initial value. So my initial amount is 12,400. And then that rate is 11%. However, remember, we can't use a percent. We need it as a decimal. Well, if you take that decimal place and move it 2 to the right, or sorry, 2 to the left, that'll change it into a decimal for you. Or if you just take 11 and you divide it by 100, either way is going to give you that value, okay? 0.11. So since you have that, let's plug it in. 1 minus 0.11 is going to give me 0.89. So this is my model, okay? That's how I can model the value of this car. So let's take a look though. There's one last piece. The real question is, how much will it be worth in 5 years? So that time frame that it's worth, that time frame goes in for T. So what we're looking for is actually this value right here. And the neat thing is, if you type it in just like that into the calculator will give you the right answer. So 12,400 times 0.89 to the 5th power. And that's going to be how much it's worth. $6,924. $6,924. And of course, money, we go to 2 decimal places. So in 23 cents. So that's how you're going to approach every single one of these problems, which is awesome for that consistency. Figure out which formula you're using, and then go and ask yourself, what's my initial value? What's my rate? What's my time? Plug everything in. So let's take a look at our next one. Cell phone use has been increasing rapidly for high school students. A recent study showed that this year, 1,560 students at Alg II High School have cell phones, and it is increasing at a rate of 4.7% per year. How many students will have cell phones at Alg II High School in 6 years? So, the vocabulary that I'm noticing is I see increasing. When I see that term increasing, that's telling me I'm going to be using my growth model. Oh. So the growth model is going to look like this. Okay, so that's the first thing that I would do is notice, all right, I'm dealing with growth here. Now let's start looking at the specific values. What's my initial value? Well, I'm starting with 1,560 students. That's increasing at a rate of 4.7. But again, I can't leave that as a percent. It said in the directions, always turn it into a decimal. So 1, 2, do the decimal over twice, which means I have to add a placeholder 0 there. So as a decimal, that's going to be 0.047. So let's plug those in. My initial value, 1 plus that rate, 1 plus 0.047 to the t. So that's my equation. That's how I can model the number of students here that have cell phones based on time. And now my time frame is 6 years. So I'm going to plug in for 6 years later, how much will it be? So again, if you do this right, you can plug that straight into your calculator. Just as I have it written there, and it will give you the right answer. Now, in terms of this, obviously we're talking about people here. Wouldn't it make sense to have a part of a person? So do I want that 0.966 at the end? Of course not. Okay, we're not going to be dealing with parts of people. So when you're dealing with whole things, okay, people, animals, anything like that, round to the nearest whole. Okay, so in this case, I'm going to round this to 2,055 students are going to have cell phones in 6 years. All right, so again, hopefully you can see the consistency here of how to construct these. All right, so one more of just like this. Miami, Florida has reported record numbers in the growing population, a growth rate of 5.6 per year. The population of Miami is 86,400. If this trend continues, what will the population be in 10 years? Growing population, growth rate. So those things right there are telling me that I'm going to have a growth model, meaning having a plus there. All right. Once I've determined that this is a growth model, now I start looking for my things like my initial value, my percent change, 5.6%. But again, you always need it as a decimal. So I move my decimal places, or my decimal place 2 to the left, introducing a placeholder 0. So now let's plug all that in. So I have 86,400. 1 plus that rate is just going to be 1.056 to the t. I'm curious about 10 years from now. So that's what I'm going to plug in for the time. I'm going to plug in 10. So I get an estimate for 10 years. So 86,400. Then I'm going to plug in a 10. And again, if you plug this in exactly as I have it written here, you will get exactly the right value using your calculator. So 86,400, 1.056 to the 10. All right, so again, we're talking about people. We're talking about a population. So we're going to round it to the nearest whole number. So we're going to have 148,989. All right, let's see if I can remember that. 1,000 or 148,989 people will be living in Miami if that trend continues. All right, so that's how you deal with all these situations. If you're given the percent increase or decrease, you have the initial value, that's what you do to continue moving forward. Now, oftentimes though, they're going to be discrete, okay? They won't change, or you'll only find values once a year or something like that. So let's take into account here. Endangered species. The table shows the world population of the Iberian lynx in 2003 and 2004. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2014? So here, instead of them giving us the percent change, they give us two values, and they're asking us to find that percent. Okay? So here, I'm going to let T be years since 2003, since that's when that first information was taken. And my Y is going to be the number of lynxes. All right, so now we have to determine the R. This time the R isn't given to us, is it? This time we're going to have to find it when we're just given two discrete values. All right, and the way to find it, that percent change. That's essentially what we're finding is percent change. And what you do is you take your current value minus the original and divide it by the original, okay? So originally there were 150, now there's only 120 a year later. So our change looks like that. So let's type that into the calculator. Negative 30 divided by 150. Our change is negative 0.2. Okay, so what that's telling me is the population is decreasing 20% each year. Okay, so we actually found our R value. The R, we're decreasing by 0.2. So here, clearly this is a decay situation. So let's see what we've got. Well, we started with 150. Is decaying 20% per year. So in here, we're going to take into account that decay. Okay, 1, and in this case, minus that rate of decay. So we're going to have 0.8 to the number of years. All right, so now let's think 2014. If we're curious about 2014, what the population is going to be. Well, we started in 2003. 2014 is 11 years later. So let's see what happens. 11 years later, what's the population going to be if this trend continues? Ouch. What that's showing is if that trend continues, there's only going to be 13 lynx after 11 years if that trend continues. Now, will the trend continue? We don't know. But just from the data given, that's what it's telling us. All right, so that's what you do when you have discrete data. When they give you two data points and tell you to write an exponential model, that is going to be your go-to place. That's going to be how you set up your structure to solve it. Two more scenarios, and then we'll be done, okay? So sometimes they'll ask you how long it'll take for the value to reach a certain point, okay? You want to know, well, how long is it going to take me to have this amount? So what you're going to do is you're going to set up the equation exactly the same way, but we're going to make a table of values to find when the function will reach that point, because we can't just plug it in. So we're going to use a table to just see how long is it going to take me to get to that value. So let's take a look at this. Rabbit populations are on the rise. Each year, the population of rabbits in Elk River grows by 7.6%. If in 2000 the population was 520, when would the population be over 700? All right, so here they give us a percent. So all we have to do is find those values and plug it in, okay? They tell us how it's changing. They also tell us it's on the rise. So that's telling me we have a growth situation. So now let's take a look. I see an initial amount of 520. I see a rate of 7.6%, which if I move the decimal to the left twice is going to be 0.076. So that's going to give me 520 times 1.076 to the t. And what I want to know, when is that going to be 700? Now, we haven't learned the math yet of how to take care of this, of how to solve it. So what we're going to do is we're going to make a table of values. Okay? I'm going to just plug in sometimes, and I'm going to see, all right, am I over 700 yet? Because I want to figure out the first year that it's going to be over 700. So let's try this out. So 520, 1.076. Oh, 520, 1.076. Let's try it after 1 year. After 1 year, 560. After 1 year, there's 560. Let's see after 2 years. After 2 years, there's already 602. All right, so we're not quite there yet. We need 700. So let's try 3. $650. We're getting closer. After 4 years, let's see how many there are. $697. So my bet is going to be 5 years. All right. But again, let's just make sure. 1.076 to the 5th, 750. So that's the first time that it hit over 700. So because we finally hit over 700, the answer is going to be 5 years from then, or in this case, they asked what year. The year is going to be 2005. So that's how you deal with the situation of, if you need to know how long is it going to take, set up a table and compare. When is this finally over the 700 mark that they told us to find? All right. one last situation, okay? One last thing, and then we'll be good to go. So, phosphorus 32 is used to study a plant's use of fertilizer. It has a half-life of 14.3 days. Write an exponential decay function for a 50 milligram sample and find the amount of phosphorus 32 remaining after 84 days. So, this is our final concept, the concept of half-life. All right? So, for half-life, we have a little bit different structure. Okay? Half-life is always going to be decreasing. Okay? Half-life is always decay. Always. Now, what is it decaying by? Well, here we're starting with a 50 milligram sample. And half-life by nature is giving us 50%. Okay, if it decays by half, that means you're only going to have half as much as you did before. So by nature, this is always 0.5 and it's always decreasing. Okay, those are the things to know about half-life. So our equation is going to look like this. So we're starting with 50. 1 minus 0.5, obviously our rate that's remaining is going to be 0.5. Now, for the time is a little bit trickier here, okay? And I gave you guys a little hint for how to deal with that. So for t, instead of using the number of days, so you don't want to put 84 days in there, you want to think about how many half-lives have passed. So here, in 84 days, how many of those half-lives have passed? Well, that's going to be 84 divided by 14.3. That's how many half-lives will have passed. So let's see. 84 divided by 84 divided by 14.3. It's about 5.87 half-lives or half-lives have passed. All right, so that's what we're going to use for t. So for t, that is what we're going to use, okay? Because when it's half-lives, you need to determine how many half-lives have passed. So you take the number of days you have, divide that by the half-life, and that gives you how many have passed. So now, to finish off this calculation, 50 times 0.5. Now, for the exponent, okay? For the exponent, if you want precision, instead of approximating that 5.87, you can actually just put in that fraction. Okay, the fraction that we started with right here to get that number, I would just throw right there because it's going to keep it more precise for you. Okay, sometimes it'll be a nice number, sometimes it won't be. So I would just plug in for precision's sake so you can see. And now, after those 84 days, notice you're going to have about 0.85, is it grams? Milligrams. So you're going to have about 0.85 milligrams left. Right, and that is how you deal with half-life. So, a lot of different situations going on, but they're all around that same fundamental principle of looking for this equation to use. Okay? So, I want you to take a moment, reflect on what we've talked about in these notes. So, write me that nice summary, and then come back to class ready to work on your practice work.